Hi guys, welcome back to my mathematics tutorial. Again, my name is Peter C. Dogwood, your math tutor. And in today's lesson, we want to look at a continuation of our previous lesson on the derivatives of implicit differentiation, but we want to blend this with natural logarithmic functions. So it's going to be like a combination of both implicit differentiation and that of natural logarithmic function. So let's look at the first problem. Y equals to the back power. This is the back exponent, There you go. This is different from t raised to the third power. T raised to the third power means t times t times t. But t raised to the third power when it is on this side is equal to t raised to the power t raised to the power t. So this means you must raise t to itself the number of times that is here, right? And then this means you must multiply t by the number of times that is on the power. So I don't know. I don't know how best to call this term, but I think it's the back exponent or something like that. So now let's go ahead now. Now to find the derivative of this, we can reword it first as y equals to t raised to t raised to t. Then what we need to do is, remember, we need to get rid of these powers, because we cannot use power rule or extended power rule. So we must get rid of these powers. So to do that, we must take the ln on both sides, right? So taking the ln on both sides, t raised to the power t raised to the power t. So we can bring this power down according to the property of logarithm. So that is t raised to the power t, the ln of t. So to find the derivative of this, the derivative of ln of y is equal to 1 over y times y prime. But the derivative of t raised to the power t, again, we need to do that. So let's do it separately. So we can say r equals to t raised to the power t. So if we take the ln of on both sides, we have ln of r is equal to ln of t raised to the power t. This t can drop. You have ln of r is equal to t ln of t. So what? You differentiate 1 over r times the derivative of r, which is r prime. Now we have two separate functions, so you can hold one, differentiate the other. We hold t and differentiate ln of t is just 1 over t, plus we hold ln of t and differentiate t is just 1, so it's not too important. So we have r prime. Now this r must be multiplied by the expression here. So you have r times t and t go out. You have 1 plus the ln of t. But this 1 means ln of e. So ln of e is equal to 1. So r prime is equal to 1 is ln of e plus ln of t. But then this r now, remember, is t raised to the power t. So when you have ln of a plus ln of b is equal to ln of a times b. So r prime is equal to t raised to the power t times ln of e t. So let's use this one. So this is now the derivative for this expression. So we can now bring in that derivative, which is now t raised to the power t, the ln of e raised to the power et, and then times ln of t. So in the first case, we differentiated t raised to the power t, and we held this one constant. So plus, now we should hold t raised to the power t constant and differentiate ln of t, which is 1 over t, times the derivative of t, which is just 1. So now y prime will just be equal. Now this y must be multiplied by this expression. So we will have y times, so this whole thing can just be t raised to the power t ln of t times ln of et plus t raised to the power t times t raised to the power minus 1. So y prime now is just equal to this. Y is t to the power t to the power t times, remember this y must be multiplied by the entire thing, not just 1, times t raised to the power t ln of t and ln of et, and then plus, so this, the bases are the same, we can add a power, so it's t minus 1. So this is actually our final answer for this problem. Let's do the next question. So these questions actually on an implicit differentiation. So we just added natural logarithm so that, because we can use the natural logarithm to assist us in carrying on implicit differentiation. So question number 15, we have y equals to the ln of x plus x squared plus a raised to the second power or raised to the power half. So we can differentiate this. Y prime is just 1 all over the entire expression, x plus x squared plus a squared raised to the power half times the derivative of what is inside. So the derivative of x is just 1. The derivative of this expression is 1 over 2. Like, bring this power down. Rewrite x squared plus a squared. And then subtract 1 from this power, it becomes minus 1 over 2. Then we differentiate inside. The derivative of x squared is just 2x. So this 2, we cancel this 2. We have y prime now to be, now because this power is negative, it's going to go down in the denominator. So in the numerator, we just have x. And then down here, we have x plus s squared plus a squared raised to the power half times x squared plus a squared raised to the power positive half. So what do? We multiply, right? We multiply this and this. We take what is inside, then multiply this and this. So is it really important? In fact, it's not too important, right? Is there anything we can bring back? So y prime is just equal to x. Let's just multiply. So if we multiply this and this, you have x, and then this is just square root. So it's the root of x squared plus a squared, and then plus, multiply this and this, it becomes x squared plus a squared. It's not really important that we even multiply. We can just leave it as it is. So this is actually our final answer for that problem. So see you in next video. Thank you very much. Please don't forget to subscribe, please. Thank you.